Thank you very much for coming. Well, I probably won't go through everything that is covering here. I might not be able to fully explain how you understand materials, but I will go through parts of it at least. But I will start by presenting myself. My name is Fredrik Henriksson. I have a PhD in machine design, which is a very complicated way of saying I have a PhD in product development. I looked at how materials are selected and used and managed throughout the product development process. Mainly focusing on consumer products, but we've done some work with industrial equipment as well. I have a license. It's based on mechanical engineering, so that's the field that I'm coming from, and my background is in design engineering. When the design and product development program started at Linköpings University, I was one of the first students there. So design, product development, all these things. I have done that since I was 18, and now let's not go into that. I've been working with it for a while now. To tell you something more about myself, this is what I do in my spare time. So trying to get stuff to fit that doesn't really fit where it's supposed to be. But I'm not here to talk about my hobbies, but I'll need to start and talk a little bit about myself. Start from the beginning, maybe. I grew up in a place called Iggesund. It's 300 kilometers north of Stockholm. It is a small mill town, and you have the paper mill. The Iggesund paper mill makes paperboard, which is more or less packaging cardboard for high-end packaging. They work with medical packaging, luxury products. I think they're working with Apple. They're working with high-end perfumes, cosmetics, high-end alcohols, all luxury consumer stuff. So this is my background in what I see as a factory and what I see as maybe the main material, because when you grow up close to a paper mill, the material that you have in school for crafts is paper, because you make a lot of waste paper when you make paper. So we got a lot of that to work with for school. So when I was about, the blue doesn't really see, but when I was about this tall, one of the first things that I remember about materials and making stuff, and I think stuff that made me who I am, is that we have craft days, I think around Easter. Mom drove me to school, followed me in, and she wanted to see what we were doing. And I think we had gotten like a plaster rooster or a gypsum rooster that we were supposed to paint, and that was the task for the day. So my mom looked at that, didn't say that much, and said, I might come back a little bit later. Then she showed up at school again, about 2 hours later, having thrown together what was approximately 5 of these big recycling bags with different craft materials, because she didn't feel that painting a gypsum rooster wasn't really arts and crafts, so she wanted us to do something else. So she had thrown together what she had in the garage and in her hobby room to make us work with that. So I started with the idea of what can you make out of something else? What can you make out of waste materials from your household? What can you make out of spare pieces of fabric? What can you make out of paper from the paper mill? What can you make out of these things? So that was sort of where I started, trying to figure out how can you make arts and crafts. Growing up, a couple of years later, I went to Linköping. I started studying design and product development, because I like design. I wanted to be an industrial designer at some point, but I realized that I'm probably not good enough at it. But engineering seemed like it was quite nice, and also I could work with getting things done, following the project to the end. And at one point during my studies, I said something along these lines, which made me spend thousands of hours for a couple of years building stuff like this. So we built race cars. This was the first year. Second year, we got really cocky because we knew what we were doing. So we knew what we were doing. We sold it to companies. We got really nice sponsorship, a lot of really high-end 3D printing materials. We didn't know what we were doing because we failed miserably at designing stuff with the material that we were using. This is a wheel. It's supposed to have something in the middle, and it had it at one point. And then at one point, it suddenly hadn't. The driver weren't too pleased with us. So we made a bit of an oopsie from time to time. So my background is, I call it a half and half. It's, half race cars, and it's half arts and crafts. May seem like two very different subjects, but what it ends up with is someone trying to maximize resources at all time, making do with what you have, trying to make the best solution with what you can find, and inventing new solutions to be as efficient as possible. As I said, I grew up 3 hours north of Stockholm. Craft supply wasn't that good, so we had to make do with things. We built race cars. We didn't have, we had some money, but not all money. Not all the money, not all of the techniques and technology that we wanted, so we had to make do. We had to adapt. And the thing that I went for that really interested me throughout this was the materials. Which materials are you using? Where are you using them? When are you using them? And why? I know during the Formula Student project as well, I saw one of my colleagues designing in carbon fiber things because he had heard somewhere where carbon fiber can be thought of as black aluminum. So you can, when you're doing finite element analysis, you can think of it as aluminum and it will hold up. The thing he didn't think of was that if you mill something out of a solid block of aluminum, and if you stack carbon fiber the same way and then mill it out, you will have totally different properties because carbon fiber is not the same in all dimensions. It is the same in 2 directions, and one of them is a lot weaker. So I saw that people are designing things in materials that do not really understand and cannot really make use of. So I got stuck on this, and that's where I am now. So there's a historical reason for why I'm interested in materials, but when I hold a course in materials and design for my students, I cannot say, because I thought it was important in 2013, I have to figure out something that's a little bit more realistic to explain to them why they should listen to me. And I have one example here. I think materials are really interesting because a lot of materials can be used for a very similar type of product or products fulfilling the same purpose. But they do affect the design very much. What you can do in wood, you cannot do in aluminum, you cannot do it in palm leaves, you cannot do it in recycled tarpaulin, and vice versa. Materials are also an interface, especially when you're working with, we've been working a lot with consumer products. So the user interacts with some materials in the product. So the tactility, the visual impression, smells. This is a ring with, I think it's actually called juniper wood. A piece of it that's supposed to be a sniff ring. So if you're on the subway, if you feel that you would rather be out in the forest walking or out in the woods walking, you can sniff the ring and feel that you're in the woods. When the smell goes away, you can just take a piece of sandpaper, rough it up, and you can do it all again. So you can revisit all of those experiences. Materials are very much experienced, interpreted by the user or the customer. You have to think about associations of a material and the combination of the material and the design. What are people thinking when they experience this? What are their previous experience, and how does that affect what they're going into with this product? And as opposed to the geometrical shaping of something, materials age. They change with time. They change with light exposure, with moisture, with wear, and of course they change with trends as well. What I tell my students that this is something that shouldn't be able to be done. They can design it because they do not have the same experience, they do not have the same connotations to the same materials. So I feel that materials are really interesting. And of course, they affect environmental impact a lot. We need to think about the processes that are needed for the material to become a product. What happens during usage? For how long time can we use the product if we make it in this material? And are there any side effects? To have a good example here. No, I don't think I have actually right now. Well, we can talk about shopping bags, and if we make them in cotton, if we make them in recycled plastics, if we make them in some other recycled material, we make them in paper. For how long can we use them, and how much energy have we used, and how much resources have we used throughout the manufacturing of the product? We need to think about all these things because, well, I think we're becoming increasingly more aware that we do not have endless resources, and we have to treat them a little bit better than we have done before. That is for everything that we design. So when I talk to my students, because I'm right now mainly a teacher, researcher as well, but most of my time is spent teaching. When I teach my students about materials, I tend to show this figure. So this is a description of a technical system by Hubka and Eder from the version I had was the late 80s. I think this is from the 60s or something in the beginning. You have a lot of environmental demands, everything from a delivery deadline to quality to recycling to maintenance. Then you have the external properties of the product. You have the internal properties of the product, then you have the design properties. This is what you can actually work with as a design engineer or an engineer. And materials is one of the very few. And materials affect a lot of the others. They affect the possible structure, they affect the possible manufacturing methods. So you have to select the material that works with everything else that you have in your design properties that fits all of these environmental demands or requirements. This makes it very complex. Material is not just a selection in a drop-down menu in the CAD software. You have to really think about what you're doing. So this is one way of showing it. The other way is something that I photographed at the, can't remember if it's the Hayward Gallery or the Hayworth Gallery in London in September. This is a sculpture, and the materials are, if I remember correctly, black marble, volcanic rock, and bronze. Everyone looking at this picture, I'd say feel the difference between these materials. You can actually imagine how different these two are to touch. That, well, while it can be explained by the figure I showed before, it's really complicated. There's something more to it than just the numbers. Especially if you're working with consumer materials and consumer products, there's something in the experiential part and the tactile part that is also really important to solve, that we need to figure out as designers and engineers. How do we actually bring this in and how do we make it work? But this is also nothing new. How materials are felt and how they are actually used in products. This is from, let's see so I say it correctly, I think this was written, it's cited in a publication from '88, but I think Sheldon and Ahrens wrote this in 1932. For almost a century at least, we have realized all of these challenges and these complexities when designing a product. So, and I don't think still we haven't really solved it. That's part of my research showing that we haven't really solved this, and we've thought about it for a century. So hopefully it's a bit complex. Hopefully it's not just that all of us that have thought about this haven't been able to figure it out. So if you're trying to understand materials, you have to remember that materials are not one thing. It's not just the Young's modulus. It's not just the corrosion resistant. It's not just the molding viscosity. It's not just the electrical resistance. It's a lot of things, and you have to think about many of these at the same time, whatever you do. And understanding a material, even one material to its fullest, is really hard. And then you have designers and engineers usually working with multiple materials. So I'd say that most designers and engineers working with designing products do not really understand the materials that they're working with. They have a hunch. They might have a pretty good grasp of it, but they do not fully understand it, because that's a lot of work for one material, and they're probably using 10 or 15 in their design work. So the ones that are implementing this are they're not fully understanding it. Makes it more complex as well, because the responsibility to make a good decision it's still there. We just need to help designers and engineers make good decisions as well. So that was not the introduction, but a bit of my view on materials. So talking about the research I've done, as said, the thesis title was On Material Selection and Its Consequences in Product Development. What did I actually do? I analyzed product development a lot. I tried to observe projects, set up projects aiming at specific things, observe them and trying to figure out, okay, what happened now, what decisions were made, and why were they made? When I looked at decision making in product development, I saw that current tools and methods for explaining material selection, or even guiding material selection, they're not really fully describing decision making itself. They do not fully explain what's actually happening and what you need to take into account. They are very much simplified to a level where I think that they might obscure what's actually being done. There is also a very intimate relationship between the product and the production system, which means that for a company owning their own production, they have very specific requirements on what they can do, and very specific possibilities of what they can do as well. Because they need to fit it into their factory, but they can also make use of the factory that they're already having. Earlier research, which was my research from earlier, pointed that there was something that seemed like organizational factors for material introduction as well. It's not just a technical part. Something in the organization, especially of a large company, affects how well you can introduce a new material. And it boils down to information is not the only hurdle to clear. A better spec sheet of a new material will not necessarily help it being introduced cheaper, better, and faster. Because there are other things that affect it as well. And when I added a little bit of decision theory to look at these problems as well, decision theory is quite, they're quite set on the part that people are not rational. As engineers, we might want to think that we're rational, and I think we can try to be, but we're not fully rational. There are things that we cannot really control in this thing. But why are current methods for decision-making material selection assuming or implying rationality? So they are assuming something that people are not. They're written as if they were programming code. People and computers are two different things. Also, decision theory talks a lot about the inside and outside influence. There are ideas of what can affect decision making that hasn't really been involved in this before. And decision theory and psychology talks a bit about mental models. In HCI or HMI, there it has been included. They talk a little bit about mental models for understanding a user interface. But can this bring something if we look at mental models of materials? So I took all of that and I made this little Venn diagram trying to explain that, yeah, there's the technology part of introducing a new material and selecting a material. There are very good tools for this. I'd say that the technology part might not be our biggest challenge. There's an organizational part, organizational change, everything like that, but it has to be applied to what happens when you bring in a new material. Do you have organizational knowledge? Do you have decision flexibility? Are you collaborating with companies working with this? But there's also the human part. At the end, there's someone probably sitting by a computer making a CAD model of the product and including the material. They are making a lot of decisions. How do we make them make decisions that are better? How do we make them include these new, better materials and not shy away from them for any reason, even if it's experience or personal identity or professional skills? What can we do to make them, well, more efficient? So I showed this, and well, let's see. Yeah, if we talk about the human parts, rationality, as I said, it's probably impossible. We can try to aim for it, but we'll never be fully rational because that implies that we have all of the information of all possible consequences throughout eternity. That is, even with big data, I think that's a big task to solve. But many methods in engineering design and design, they imply some sort of rationality. You should weigh all of your requirements according to some rational model that you have because you fully understand the weighing of these requirements. If we also talk about humans, developers and designers, they of course have habits. They have intuitive preferences for certain solutions. They try to design it one way or another. For myself, as I said, I grew up by paper mill. Most of my early days was with arts and crafts, working with paper or discarded cardboard. I realize now, when I design things, that I usually think of it as, how would I make the paper model for this? And then I make it into something else. Someone who grew up working a lot with Play-Doh and clay would probably think in a solid block and then trying to cut away things in order to make the model. That works if you're doing something that is milled out of a solid piece. But if you're doing that and then making it into sheet metal or carbon fiber, or making it out of a textile, then you have to convert it another time. And the way you set up how things should be done is probably not the best way for that material when you're there. So you have some sort of idea, how do these actually behave and how can I make it fold into the way I want it to fold? And then you have mental models. That's a personal understanding, not equal to the objective reality. I drew a very nice figure looking like this. These are two solution spaces. The gray one, I'd say, is the solution space, the objective solution space, all the possible solutions for something that we can do. The blue one is the perceived solution space. This is what the engineer thinks that they can do to solve the problem. The light blue part here, that's revisions. That's when you design something and figure out that this won't work. I have to rework it. Here is where everything that has ever been designed has ended up. This is unused design space. This is something that can be done that people will not do because they do not think that it's possible. And that applies to materials as well. If you don't think that whatever material you have can be formed in the way you want it to be, you will never look for it. You will probably not do a full search every time you're trying to solve a problem. Okay, I need something that has this, I need it to have this working temperature, or working temperature span. You will not look for all materials possible in the grant EduPack every time. We try to tell students to do it, and they still don't when they're actually assigned to do it. When people are trying to solve problems at work, they don't go through everything. They go through what they think they can solve the problem with. Oh, yeah, I remember these plastics probably work, so I'll look for those first and see if this seems to work. If it works, you're in here, you're all set. Then you're just going to continue. Find something in here, then you do another search until you get in here. But if you don't know, it's the awareness and knowledge. There are things that you know that you know. There are things that you know that you don't know. There are things that you don't know that you know. And there are things that you don't know that you don't know. This is usually the things that you don't know that you don't know. And of course, there are mental models of materials as well. I perceive ABS plastic to be something, and I can do certain things with it. I perceive other materials to be in another way, and someone who's worked with ABS for their whole life will probably have a totally different understanding of the material. That's also that these can be larger or smaller depending on the experience and the knowledge and skills of someone who's working. But all of this affect product development and affect the design that you can actually end up with. Because, as I said, if you don't know that you're looking for something, or if you don't know that something is possible, you will never go try to find it, or you will very seldom go and try to find it. So, going from humans to the technology part, there are challenges there as well, of course. There's the perception of materials in terms of tactile experience of materials. They're challenging to quantify if we're working with something that has a physical user interface. Soft metrology exists, but it's complicated. There are a lot of contextual, there are a lot of personal reasons, and especially in this room, there might be materials that are changing when you add something else. If you add electricity, if you add water, if you add heat, how will you actually be able to perceive the change in a material when you add something? Are people able to understand that? Usually, not really. As a consumer, and how do you make something that people will actually understand that they can use? When you're investigating novel materials, there's a challenge of the non-comparable data. I had students explaining this to me in the best possible way. And I don't think she actually understood what she was saying. I don't think she understood how good it was. Because she came to me and she said, okay, we're working with this design and we're designing, I think it was a car seat at the time, and it was a back piece. And I have these two materials. Can you help me, Fredrik? I don't know how to or choose between these. Okay, I said, so what do you know about them? This one, it's really nice, it's young modulus, it's perfect, it's lightweight, and we can make the production work really well. Oh, that's great. This one I can get in a perfect shade of blue for the branding of the product. So how do I compare these two? And I just looked at it and I said, I have no idea how to compare these two. Because it's non-comparable. Which is most important? I think we went with the producible material, but you end up with this, especially when you're developing new materials, because you don't have all of the material data. So you make do with what you got, and usually say that designers are opportunity maximizers. They're looking at what is the best possible solution if everything goes right. And they can take a lot more risks. Engineers, design engineers or mechanical engineers especially, are they're risk minimizers. They're just trying to make sure that nothing fails. So you have a lot of mechanical engineers discarding a lot of possible materials because we don't really know about this thing and we don't know if we can get it through production then. So that makes it really scary. I'll probably go for something that we know will work. It's a perfectly reasonable way of going about working, but it will make a lot of novel new materials and good materials. Implementation will take a long time if you have a lot of people doing this, because materials will be left on the shelf because we don't know enough about this to be able to introduce it into our production system. And of course, there's a lot of production system challenges, because new materials, you can make new geometries, you need to revise the fasteners, you need to work with tack time. There's a lot of things that you need to think about when you select a new material. And the challenges might be both upstream and downstream of where you're introducing this material, which also makes it a bit more challenging. Also, experience from industry, we looked at a solution where the roof panel of a car would be in a material that was non-weldable to the rest of the body. So it was not going to be in steel. Okay, that seems to work perfectly fine. Problem was that then we couldn't probably get it through paint. So, okay, then we need to install this in the beginning of the assembly line after paint has been worked on. Well, that will work. Probably need to use adhesives because we don't want like bolt heads to be shown on the product. Will work well. We have an adhesive that works for the windscreen. That will probably work perfectly fine, and it did. So they glued this panel to the body, and for the life of them couldn't figure out why the panel was wonky for every fourth or fifth car getting out of the factory. Problem is that adhesives take a lot of time to cure. And they had checked the next, I think, 5 cells. So nothing in the robotic system was actually going to be touching the roof panel. But one of the stations was installing electronics inside the cabin or the cockpit. So someone had to climb in. And one of the guys doing this was about my size and about 55 to 60 years old. So, well, safe to say, not an athlete. And he tried to get in, so he had to grab somewhere to be able to get in and out of the car. And it was my size in length as well, so pretty big hands. So he grabbed all over the roof pillar and onto the panel that was still not cured in place. So every time he climbed into or out of the car, he moved the roof panel. That took some time to figure out. And that is an example of production system challenges that is not really related to the material. You can do a lot of visualizations, you can do simulations, and you can think about this for all of eternity, and it will still fail when you get to production because someone will do something that they're not supposed to do. So this is also a type of challenge that you need to figure out when you're introducing a new material. It makes people a little bit hesitant, so you need to convince them that they can actually work with this. And there's an organizational part as well. Introducing new material might demand a little bit of a less linear process than other development work, especially if you're in a large established company working with the same products that you've done for a long time. yeah, they say that they're working agile and they're working flexibly, but it's a pretty linear process because they kind of know what they're supposed to do throughout everything. But if you're introducing new materials, you might have totally different challenges that need to take into account. And also you need some sort of organizational flexibility. You need some sort of slack to be able to manage if you need other decision-making paths, for example, if you need to make new sub-organizations. Also, an example from automotive industry. We also looked at the roof panel, but we tried to get it through paint this time. It was still not weldable in the body shop, but we could make it with some fasteners. We could make it fit, and we could make it go through paint, paint it at the same time as the rest of the body, then remove the fasteners and actually adhesive join it to the body. Same way as we tried to do it the last time, but this guy the guy who was installing the electronics had been moved to another place, so he was not moving the panel this time. The problem was that, has anyone of you seen the paint shop in the automotive industry? So the basic thing is that before you paint it, you run the body through solvent baths and cleaning baths. And some of the times you take your vehicle body and you just put it down in here, throw it up, do it like that. Works perfectly fine. Some people think that it's more efficient to tumble it through. So you'll be able to use less solvent and get it as clean. Problem is that the roof panel in this case will become one big, scoop or an ore. A roof panel in steel welded to steel body in white, that's not a problem. Welds are overdimensioned. They will solve this. We would have some sort of flexible thing because we had an aluminum body panel that cannot be welded to the steel body. So we needed to have some sort of distances and some sort of, a bracket or whatever that we could remove afterwards. So someone should probably design a bracket for this. We probably need to figure out what kind of load will this be able to take. So I talked to colleagues in production and they said that, we have no idea because we have never thought about this. Welds work, so why would we think about the loads? But there seems to be, the aerodynamics people, they're doing some sort of analysis like this. We can probably talk to them. So I said, great. So how do I get in touch with them? And crickets. Because production does not have communication with aerodynamics. Because why would they? That is just a waste of time until you need something like this. When you're running with the same type of product and developing the same thing that you've done before, you have optimized your organization to become a little bit rigid. And when you introduce something like this, you might realize that the organization is a bit too rigid. Because this took me 2 weeks to figure out how to contact someone at Aerodynamics so I could do this analysis. Then it took 45 minutes to figure out how to do it in a meeting with them. So I spent 80 times as much time trying to figure out how to contact them as to solve the problem when I had them in a meeting and could build a cardboard model of what I'm trying to do and show them, I want to know the load of this panel when we're doing this thing. And they said, we have the model, we have this. Yeah, so if you can just figure out how to pay us, we'll do this when we have time. And it will probably take a week from when you're ordering it. So, yeah. But as I said, organizational issues were definitely what faulted this through for quite a long time. And then an organization, of course, have organizational power. I will not say power struggles, and I will not say power challenges, but people have implicit and explicit power over decision making. And that will also affect these types of things. Because if someone feels that we're not a company working with this type of material, okay, then you'll probably not be able to introduce it. And that might be someone who's not really in charge of that decision making, but they might be in charge of production, or they might be in charge of simulation, and they don't know how to introduce this in their process, so they will not do it. So, the conclusions I made from my research was that there's a risk of acting rational, because you're only acting, you're not actually being rational. There's a challenge of the multidisciplinarity of this. There's possibilities and there's opportunities as well, but it is at core multidisciplinary problem that you need to solve. And you need to figure out developers and their preferences, because developers and designers, they will work in their own way, and you need to not work around them, but work with them. They have mental models of materials. This means that more information and a better spec sheet is not the only answer. Having developed a better material is part of the job, but you also need to sell it and convince the people working with it. You probably, if you introduce a new material in your company, you need to be able to change the development process. And both for companies introducing new materials and for companies producing them, I would recommend making some sort of material vision, showing what the material, both where we want to go as a company, but also with this material, what can we actually do? The contribution here, let's see if this... the important part here is that through industry, you need lifelong learning of how to work with new materials to be able to adapt to the new materials that are coming out. And I'm working on this part, the educational, that we need to work with explaining the complexity of product development so people actually understand it when they come out and work in industry. So what are we doing to teach the engineers how to work with this? Well, Grant EduPack, there's a lot of material data. There are databases that we can work with. They're really great. But they're only numbers and graphs. Great thing. Will maybe not convince that many people. We try to work a lot with the labs and workshops, having students actually interact with material, building things in them, trying to understand that. Prototype, what can we actually do with these materials? And we have what I have on photos here, which is a physical material library that we introduce our students to, as many as possible every year. And I think we're now at 3,000 plus material samples. With full inventory, some material data for every material sample. And they have a QR code so you can actually go in and look at the material data on your phone, for example, when you're a student working here. So we're trying to expose them to as many materials as possible. Have them in here, browse, go through, search for a material, they can do that, or they can just open one of these drawers and see what's in there and trying to figure out, okay, is this something that we can work with? Because they need to understand how many materials there are and how different they are so they can start working with this. And if you have anything that you want us to show students, I'm happy to be in contact, because we always try to add materials in here. And we also connected it to the library, so you can search from home as well. Okay, I took a photo of this material, what is it actually? So we're trying to make it as useful as possible for these students. So if you want to introduce a material as a company, some questions that you might want to think about is your organization prepared, both upstream and downstream of where you're trying to introduce the material? Can you actually take advantage of the material properties right now? Or do you need to educate people? Or what do you need to do? How can you reduce the risks? And how can you learn about the material? Can you do some sort of tinkering? Can you have a workshop where you're trying to learn about the material, where it's not used in something that should be launched in half a year? Can you do some sort of skunkworks project that you're trying to work with that is not connected to pure product development? Or can you recruit? That is something I know some automotive industry companies have done that before. When Audi tried to work with aluminum, they tried to employ people who had worked with aluminum before. When BMW started working a lot with carbon fiber with first the sport models and then the i3 and i8, they recruited people because they said that we need people who know carbon fiber and are not BMW people, because we need to develop this in a different way. So they went out and, I was going to say bought, but hired a whole new division to do this. Might be a little bit complicated, but recruiting might be a thing, for some time at least, or connecting to other companies. So remember that this is an important part, but there's also the human, there's also the organizational part, and you need to solve that if you're trying to introduce new materials. If you're developing a material, you need to think about what does the designer or the engineer need to know? What can you do, and how can you convince them to use your material? And I think show and tell, beyond the material samples and a spec sheet, is really important. What you can work with to show that we have materials that can solve all of these problems for you. Getting all of that in a list, it's good, won't help to convince someone maybe. So you can work with something that is called material-driven design. It's another way of developing products, but you start with a material and you end up with a product. So it's not the classical problem-based solving. So you work with understanding a material, creating a materials experience vision, trying to manifest this in some sort of pattern, trying to figure out what kind of product do we actually do from this material to show it off as best as possible. And then you do, this part is usually that we call product development. So here you develop the product. Well, if you're developing the material, it could be you showing this, or it could be working with student projects. As I said, I'm a teacher, I work in university. I need to recruit projects for next year's course. No, but we have done this type of thing throughout a couple of years at university. So here we worked with solid pine wood, something that is, of course, used today, but often in fairly low-cost, low-value products. They're not made into furniture. They're made into construction material, for example. So with students looking at the material, tinkering, they did everything from chopping it up and making sawdust and adhesive balls and try to figure out what to do with that, to staining it with everything from tea to red wine to strawberries. Strawberries does not work to stain wood, if you ever thought about it. It does not have the pigment enough to do it, but it was interesting to see what would happen. Blueberries, that really works on the other hand. They tried to do everything. They tried all different types of surface treatments, all types of construction technologies, everything to see what would happen. And they made this, emphasizing both on the grains and the visual structure of the material and what happens with pine if it's left untreated in the sun. Because this is totally untreated, and if it's a lamp, it should yellow. So this will be yellowing with time, because they wanted to show that the material has aged, that it's not a new product, because that's something that you can sell with it. This will change over time. It will not just become worn out. It will actually change. Still pine, but they try to work with scrap pieces, this project. And what they ended up with was a new manufacturing technology. So taking these scrap pieces, aligning them in this sort of cross manner, making a new, it's a It's not called a glue beam, but I'm trying to figure out what the name of it actually is right now. Adhesive joining these together with this cross section, and then making the round pieces or circular pieces. So you get something that is the color of pine. It looks purely like wood, but it's zebra striped throughout. And you can do that with the flat sheet parts as well, because you work with prim wood in this case. So you get something that looks very much like a natural wood. It is fully natural, it's solid wood, but it has a totally different visual appearance due to the manufacturing technology that they used to figure out how to work with scrap pieces. How can we actually make something out of the pieces that would be thrown out of a regular furniture factory? Then we have some other projects with other materials. We're not just working with wood. Here we had a company working with graphene-coated textiles. It's a master thesis, and they went to Luis, who did the job, and said that we have all of these great materials. And we have done some projects with customers, but we cannot show them. We cannot show these projects. We need something to show prospective customers what you can actually do with this material. Can you develop a product portfolio for us? And she went haywire with this. I think it was 9 different products in the end. Everything from handlebars for a stroller that were heated and had an automatic brake in them. So if you lost the stroller, it would actually stop. To these sign language interpreting gloves, because you are able to fit sensors in them to make sign language and interpret that into text in an app. Because sign language is not the same throughout the world either. So you have American Sign Language, you have British Sign Language, so even if you sign, you do not necessarily know what other people signing is saying. So here you can fully sign, and you have, I'm just sad she didn't call the app Babblefish, but that might be that I read The Hitchhiker's Guide to the Galaxy at the wrong stage of my life, I think. No, but this was something that they explored, and she also did heating things and heating blankets. So a lot of different products that showed what the material can do. And here we have another product that is recycled LDPE with wood grain fiber. recycled LDPE is abundant. We just don't know what to do with it. So they had these students had a company trying to figure out, okay, we can make the material, but what the hell should we use it for? So they went to the students and they did this material-driven design project. Ended up at, well, it's good. The material doesn't really it becomes more sustainable if you include a lot of wood fiber. But the color and the texture is not really something that customers seems to appreciate. And we have way too much of it to use in any single customer appliance. So what if we make it even more sustainable by making voids for concrete pouring, for making concrete slabs for housing? The concrete slab only needs to be solid where the walls are. Through the rest, you can work with a lot less concrete, so you can do these voids instead. So all of these 4 projects are done with the same basic methodology, and the students more or less getting, here's a material, here's the process, do whatever you want, and try to convince me that it's good in the end. We try to help them throughout the project, but we don't usually give them that much more. They start with the material and trying to figure out where it would fit. So you can end up in very different places depending on what the material actually is. And what they've been trying to do then is to see, okay, we have a material here. What's the best set of environmental demands that would fit this material? Where will it be placed in the world? Yeah. Let's see if I have anything else. No, that was actually the talk.